Afternoon, everyone. So today I'll talk about my PhD project on the geochemistry and petrogenesis of the Mafic and Ultramafic rocks and the associated chromium Ni-Cu-PGE mineralization in the Superior Province. My name is Klaus. I am supervised by Dr. Mike Lesher and Dr. Lulay from the GSC. Well, this project is supported by the TGI from the GSC, and we have also support from the as in-kind contribution and in terms of access to samples and facilities from the Ontario Geological Survey and from Quebec Geological Survey, as well as from Valley, Azimuth, and Oront. So the problem of my research is that Archean magmatic nickel copper PGE and chromium PGE, so they're a majority of them are hosted by high temperature climatic Mafic rocks. However, they are very non-uniform distributed. For example, here in the Superior Province, in the Abitibi Wallace province, we have numerous small to medium high grade and on large low grade nickel copper PGE deposits and rare chromium PGE deposits, as Shebandowan is the best example in the Abitibi. And in the Bird River Uchi, Oxford to La Grandissima, which is classified as superdomain and nicknamed as Boogie. We have the world-class chromium deposit in the Ring of Fire, Black Thor and Blackbird, and some other small chromium prospects in the James Bay area in Quebec, and economic nickel copper PGE deposit in the Eagle's Nest. Just for comparison, like in the Northern Wiluna Belt in Western Australia, it contains like numerous world-class nickel copper PGE deposit, but negligible chromium PGE deposits associated with these nickel deposits. So we think this is a factor and represent a confluence of several factors such as low magnesium, high chromium climatic magmas, and high magma flux, and different access to crystal sulfides and oxides to upgrade to this upgrading this ore deposits. So my research is based on I'm working on a province-wide compilation on the geochemistry of the Thematic rocks, and also starting on the iron formation fascias with the spatial distribution in the Superior Province of the different iron formation fascias. This last summer, I could finally go to the field and work on the Shebandowan area and also in the Ring of Fire, specifically in the Blue Jay feeder. And also, like this, now I'm working on the sample prepping and to work on geochemistry and petrology. Apart from that, I'll also work on thermodynamical modeling and on the silicate and chromite to sulfide phase equilibrium. So this is we talked about this was approach on the last Metal Earth meeting presentation, so I'll skip that for that due to our time today. So basically, the compilation work I compile around 20,000 samples and filter out all the undesirable samples and to around 10,000 unique samples of chromatic affinity rocks. And yeah, they are mostly concentrated in the Abitibi, of course, because like most of that there is a well-studied area with many data available, but I'm still working on that. So I expect to have much more data for the other sub-provinces and the other chromatic areas. So I'll just skip for this and go and focus today on the two areas that I worked in the summer: the Shebandowan area in the Wallace province and the Ring of Fire. So the Shebandowan, it was a fast-producing mine by Ni-Cu. So basically, in the area we have a distinction between ultramafic seals and ultramafic flows, and also some interflow magnetite or hematite iron formations. The thinner seals and flows here, they're less differentiated, whilst the flows here and the seals, the thicker seals here, they are mostly differentiated from Haslergites to gabbros. All of these alter to green-schist fasces, and they're really deformed by a main fault, which I'll show here. Is the Crayfish Creek fault zone. This is a dextral fault zone, very high strength fault. We see that it disrupts pretty much all the stratigraphy in the area, and it makes it a bit harder to determine magmatic phase direction. But from core log field observations and information from other areas south of the Shebandowan mine area, we can imply that the magmatic phase direction in Shebandowan is towards south, because we can grossly establish that we have dunitic peridotites at the bottom that difference toward hornblende gabbro in the top, and down south of the area we have pilolavas that give us tops to the north. So we have the mining area occupying a synclinal trough, and to south we have the anticlinal, and the late felsic intrusions also occupies a anticlinal dome. This is more or less how the rocks in Shebandowan looks like. This is a oikocristic peridotite from one of the flows. We can see that they're mostly undifferentiated. This is most of the rocks are much more altered than that, but like here we can see that we have like a olivine and later OPX and CPX oikocrysts, as well as some chlorite to thermalite, chlorite amphibole alteration here that we can imply is less trapped liquid. As in cross portals, you can see that's pretty much everything is serpentinized. On the mine body, one of the seals, we have pretty much the same aspect with some disseminated chromite within it. And on the bottom of the body and towards the upper part of the body, we go through some very altered gabbroic rocks. The geochemistry in the Shebandowan area shows that these ultramafic rocks, they plot within a well-defined olivine accumulation line here, as you can see. So, like mostly of the Shebandowan rocks will vary from 44 to like 13 NGO%. These are rocks from out of the mine seal. And in terms of iron, in comparison with the Abitibi rocks, for example, here, the Shebandowan cumulate rocks, they are much more high in iron. So this implies that they discumulate rocks. They contain lower phosphoric olivine and might be derived from lower magnesium magma, as in comparison with the Abitibi. Ni-Cu to MgO also show the same olivine fractionation accumulation trend. We have some of the samples that plot off the trend, but it's mostly because they are olivine sulfide cumulates. Of course, this is a mining area, so we have a bunch of that. And the most interesting is the chromium content in these rocks. We can see that in the Shebandowan ultramafics, mostly are differentiated toward, we can see another fractionation accumulation trend, but we also can see that this sorry, this accumulated towards a chromium saturated accumulates, but in the meantime we also have some olivine accumulates here. This is probably indicates that the magma evolved from an undersaturated to saturated in chromite, but like we have to go deeper than that to investigate it. This is an overlook on the mineralization in the Shebandowan area. The sulfides they vary from massive sulfides toward rich sulfides into some neck texture patching, neck texture sulfides. Most of the rocks in Shebandowan are of the ores in Shebandowan are breccia sulfides because of pretty much because of the influence of the deformation from the main fault. So we have breccia sulfides with all kinds of inclusions within it, from granites, peridotites, and everything from the surrounding rocks. We have it included within the breccia sulfide. The massive chromatites in Shebandowan, they are intersections up to 15 meters thick, but they average pretty much to 1.5 up to 3 meters. And they are like pretty long and like extending along strike of about 4.5 kilometers. Mostly of the chromite in Shebandowan are disseminated chromite, but really our attention to Shebandowan is this because it's one of the single occurrence within all the Abitibi walls of province that we have such a quantity of chromite that we cannot simply get by crystallizing a chromium saturated magma. So it's not a peptidic, chromite. Next slide. Okay, so moving on to the chromites in Shebandowan. So their chemistry shows that like we can pretty much distinguish them in terms of the flows and the seals in terms of aluminum content. So in the seals we will have more higher aluminum rocks, whilst in the ultramafic flows we'll have lower aluminum aluminum amounts in the chromites. So this is maybe like influence of different oxygen to gas, different pressures in the flows and seals, and also since it's pretty much everything very altered and serpentinized, so we have a trend in the increasing iron content within the chromites, mainly because of alteration, and because of that, like we have a very low chromium to iron ratio. That's why the company in the past never decided to produce chromium in the area. So because like in places like Stillwater or Chemi, with where we have economic chromite, we can have chromium to iron ratios to about 2 to 1.8, 1.7, and so on. So the other area that I worked this past summer was in the ring of fires, most specifically in the 8-12 prospect, as we here named as Blue Jay. So Blue Jay is it's kind of interpreted as a feeder, like a trough-shaped feeder for the black tor intrusive complex. Here we have in this map we have a bit of a reconstruction of the original positions of the region geometry of these intrusions, but you can see that this the north is indicated, it's indicated toward this direction because everything here was strictly rotated. And so the host rocks here in Blue Jay, they are pretty much the same as in the Black Tori Venus complex, from dunite to like a crisperiodotite up to some the brick rocks and the chromatites. And we have the late Websterite intrusion, which is a late melt that have intruded a semi-consolidated black tor, and also made a produced brachiation within this conduit here, and has this produced some hybridization within the rocks, lots of chromatite and dunite classes, as well as antoliths, xenocryst derived from upstream, and hybridization of the ultramafic rocks. So this is more or less like how the rocks looks like. This is the host rocks in Blue Jay that goes from dunite. We have the crisperiodotite and a more pyroxene-rich rock, and some of the semi-massive chromatites. Late Websterite intrusion, we have differentiated from OPX-rich Websterite, and it goes towards gabbro. We have also leucogabbros, but like just the most differentiated rock I've seen was the melagabbros. And also here is an example of Websterite intrusion in some of the previous black four holes rock. We can see that we have a disrupted neck texture. We have a neck texture orthoccumulate rock here, with neck texture sulfides, and injection of the Websterite here dissolved pretty much of this sulfides in olivines here, and maybe it have compromised a bit of the ore grades for the mine guys. And as a final product, we have lots of hybridized rocks with lots of different classes and classes, and also xenocryst derived from upstream. For example, in here we have like a periodotite with different variations of olivine size and olivine aggregates, and we have in here dunite classes and chromite, so classes within an oligocrystic periodotite. So this is all derived from upstream by a different kinds of mechanisms, from mechanical disaggregation. It might be reaction with the magma, or olivine chromite reaction. So it's a lot of mechanisms to explore. So the geochemistry of these rocks shows, like as Shebandowan, it shows a very nice olivine fractionation and accumulation trend here when plotted against titanium. But overall, these Blue Jay to black label rocks, they are overall less titanium rich. This can reflect difference in the source in the source compared to B2B, but from major elements is not enough to talk about that. And here I plotted against silica, we can see the same fractionation accumulation trend, and also some of the chromium-rich rocks plotting towards the chromite field. So In terms of chromium content, we also see a trend towards chromium saturated content, but here we are mostly due to these rocks here being enriched, like having those chromium, this chromite class within it. So this is probably due to those chromite and antiliths. And also in terms of iron content, we have relatively higher iron contents in Blue Jay compared to BTB. This is we can see this higher iron content in the more chromium saturated rocks, but we also have some chromium poor cumulates that contain the normal iron, but more phosphorate rich component, a more phosphorate rich component here. So for the work in progress now, I'm working on sample prepping and the petrography of all these on both areas that I talked about. And in the meantime, I always bring up more data and compiling more thematic chemistry and also our information fascists from the Superior Province. And and also working on some Python scripts to extract some phase equilibrium experiments for chromite, especially when it's alone in the liquidus, using the MELTS database. So for next summer, we probably have a follow-up field work to collect more data, and for the future, we go through the geochemical and thermal erosion modeling, and also improve the phase equilibrium modeling. So that's it from me. Thank you very much.
Great. Thank you very much, Klaus. I think we're just going to push ahead. And if you have